All right. Hello, everyone. Welcome back to the double operatic theory of systems lectures. Today, we're going to look at the compositionality of behaviors. We're going to continue looking at the compositionality of behaviors, and we're going to focus on generalized Moore machines. So by a generalized Moore machine, I mean the lens-based systems we've been seeing. So let me first describe, or like recall some of those, right? So we've seen generalized Moore machines here. Are as we've seen before, so a theory of generalized Moore machines is a fibration of categories. So we think of this as being a notion down here of a category of state spaces, of potential state spaces, or just spaces. And then up here, a fibration of bundles over spaces. And then we have a notion here of what we might call the tangent bundle, right? So e.g., we have if C is a category with products, finite products, then we have the so-called simple fibration. And the section being the diagonal. So this is the simple fibration. And we I believe talked about this before, where up down here we would have things like A plus, and the simple fibration consists of product projections like this, and the maps in the simple fibration are of this form. Right. So if C has finite products and F, C to C is lax-monoidal, lax-symmetric monoidal, which means we have something like Fx times Fy to F of x times y. Then we can get, then we can also take this to be the simple fibration. And then we can take this to be instead blank times f of blank. So if the diagonal here is blank times blank, so we send A or S, we send it up to S times S, mapping down to S, so is T. And S to S. Right? And oh, I should say that I generally call these things tangencies because it's a notion of tangent bundle, if you will. Okay, and then 3, we have something that's much more like a classic thing. If we have a if C is a tangent category, then we can take essentially these we can take C arrow, but this will be something like a so-called display map. We need this to be a fibration. So we need some kind of notion of map that pulls back. So we can say with display maps that are stable under pullback. Then we actually just have the tangent bundle functor here, T, such that such that the tangent bundle TS to S is always a display map, then we get this. So e.g., we have manifolds. We have, say, something like submersions, which are a class of morphisms in manifold that are stable under pullback. We have here the codomain vibration, and here we have the tangent bundle functor. So these examples of tangencies give rise to the following three examples of Moore machines. So in a tangency E, B, T, a Moore machine, or let's call it a T-Moore machine, with interface I in E is a lens, let's call it, it's a span. TS, or, in E, where this leg here is vertical and this leg here is Cartesian with respect to pi. So this is what we've been saying before, that this is a kind of lens. So is a lens in E. So before I've been writing this with the bundle notation like so. Right? So in all of our cases, let's write down what that is. So in C semi-direct product C, or the simple fibration over C with the diagonal, right? An interface, so we have, let's say, an interface is a pair I-O, both in C, and the system is going to be two maps, right? There's going to be a lens, as we've described before, UE, SS, IO, IE. It's something like a pair of maps like this. E goes from S to O, and U goes from S times I to S. So in the tangency with respect to a functor here, then an interface is still just IO in C. And then now, right, it's UE, but now it's a lens of the form FSS. This. So i.e. we have E goes from S to O, and U goes from S times I to F of S. And this is useful because F could be something like the power set functor, which would give us a notion of non-deterministic Moore machine. So this is the classical Moore machine here. This here is a F Moore machine, we could call it, including non-deterministic or stochastic, depending on our choice of functor. And then here for something like, let me say, submersions over manifolds, T, right? Our interface here is now a submersion, I to O. And then our system here is something like this. So i.e. we have E from S to O, and we have U, which is a function that takes in a pair of an S and an I, such that if I call this pi I, or if I don't know, little I, maybe? No. P. Such that pi equals ES, and we get a tangent vector at S. So that's just reading out the commutativity of this left-hand side here. The pullback here can be described as this set. And U is a function that takes it to the tangent bundle, but it has to live over this projection. So this has to equal this. And what that means is that if I look at where we get a tangent, U gives me a tangent vector for everything in here. Everything in here goes to a tangent vector, but that tangent vector is tangent to S, the same S that's in the first component here. So this is one way to write out what you get. And this gives us a nice notion of a system of ODEs. Of ODEs, you know, with what we might call kinematical equations, which describe our manifold. Okay.
Sorry,
So
just a small thing. The interfaces for the first two examples live in C cross C, right?
yes. Yeah, they live in C cross C. My point here is that they're just two objects, i.e. both I, O are in C.
Right.
They're just two objects of C. Okay. So and we've seen before that in these examples you have these notions of clocks. And indeed, let's look at these three examples in turn. So in the first one, we'll say, I'll give them names. Of course, we'll have to specialize this to determine which ones we really care about, right? So in one, our clock for these discrete time, discrete space dynamical systems or Moore machines is going to be +1 id, which goes from n, n to n star. In other words, this is a system that takes no input and simply updates the state by 1, right? And so now we can say what does it mean to describe a behavior of a system? Well, so we'll say this. So given a map, which I'll call, OI, in the top of this vibration here, right? So this is what we called before. And so I've called this a chart for the reason that we're going to chart out the trajectory our system is about to take. So what is this? i.e., this is a family of two things. It's a map from N to O, and I from N times star to I. And of course, that's might as well just be a map from N to I. So as you can see, one of these things is simply a trace of inputs and a trace of outputs, right? So given that, we could write that here. We have N, star N. We put such a thing over here, I-O, and then we put our system over here, and then we can ask, is there a map is there an S such that SS living here makes this square commute in the sense of being a map of spans? So just to be very clear, right, what we're saying is that there's a map of in C cross C, these are both some kind of spans. This is a single map. And then what we're asking is, does there exist a map like this that makes this commute? Okay, and so I think we covered this before. This is that question. Just could you pause it for a second? All right, excuse me, I had to just get my notes. Right, so for this example, the second example, where we need to choose a specific kind of functor to use. And so the functor I'm going to use here is going to be a probability functor. I'm not going to be too specific with our actual kind of probability functor and foundations one right here, but I'm going to say that for now, let's take C to be measurable spaces and F to be the so-called gyrimonad, such that F of some measurable space, X, so measurable spaces is the set of X and its sigma algebra of measurable sets. So we'll say Fx is the set of probability measures on X with itself equipped with some kind of sigma algebra. I'm not going to go into it. Presumably this is due to Giri, but I think it was first written down by Levere. Okay. So, right. So so first of all, let's just ask ourselves like what a system here is, right? So a system is going to be some state space, which is a measurable space, together with some measurable function like this E, and then some other measurable function, but let's ignore that for a second, into f of s here. So what do we call U? If, in other words, U of Si, we can think of as being is a distribution on states, which we can think of as a conditional distribution. So S prime given Si or given that what we might say that so we might think of this as describing the distribution of next states given that the current state is S. So S and I. All right, there. I'm not going to be totally formal about this. Right, but in order to make sense of what we might want from a behavior here, so we want to ask like, what would a behavior of such a stochastic system even be? Right. So before we go into the representability, let's just consider. So let's just consider the closed case, which is that IO is equal to star star. It's closed, right? So in other words, we have a box like this with no wires coming out for S, so that we just have U, which is S to F of S. Right? We just have some kind of probability in U. So a behavior, right, is a sequence of S valued random variables. X1 dot, maybe S1 dot 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 Sn dot dot dot, right? Which sort of update to each other, right? This is the idea of the sequence, but it's worth noting that we have to be a little more careful about what we actually mean when we have such a sequence, right? Because we have to discuss what it would mean to push forward a measure or to understand the expected value of a random variable. Like, what is the law given by the random variable? So I guess let's take a little bit to cover that. Actually, just can you pause it again? Okay, after having a think about this, I think I'm just going to take the next lecture to go through this example in greater detail so we can actually sit with it and have time with it. But so for now, I'm just going to say that if we take the following clock, so this approach is due to Owen Lynch in a joint paper with Igor Richel, Sam Satin, and myself. And so if we're going to take the following measure space here, which is going to be, we're going to take the what we call omega hat, which is going to be the sum, the coproduct for n and n of omega to the n, f to the n, where f is our sigma algebron here. So this is going to be a coproduct in measurable spaces. It may be equivalently described as omega to the n times n with the induced sigma algebra structure induced from omega star, which is the coproduct of list of elements. Okay, so that's the state space, and now the update here is going to be a very similar to the clock system. We're going to take our we're going to take it to be id, and we're going to take it to be +1, but +1 is going to mean something special here, because +1, or let me call it C sharp, C sharp is going to take a current element, and it's going to give us a distribution of new elements. And the distribution we're going to take is going to be defined by C sharp of n comma w is going to be the following sequence. It's going to be n plus 1, and then we're going to take w, which is a sequence of things. We're going to take the sequence here, w1 dot 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 wn, comma wn plus 1 prime dot dot dot, and so on, where the wi prime are all drawn from the probability distribution on omega. On omega. So I should have said somewhere, we need a sample space. So that's going to be omega, f, and a probability distribution on it, p. And so what this will represent then, so a behavior here, so a behavior will be a sequence of random variables whose law evolves according to this Markov process. Subordinate to the filtration. Let's call it Fi, where Fi is the inverse image the f to the I. So we take omega hat and it goes into I for all I. We have these projections. And we just pull back. And that gives us a filtration. So one really cool thing about this one is we see that sort of it's not just that the time ticks up, but we also sort of resample from all future possible things here as we go forward. So I'll cover this in greater detail tomorrow, which will also give me a good chance to actually brush up on it. So, okay. So the point being that sequences of random variables that evolve according to the law of a Markov process are representable in the sort of classical theory of non-deterministic Moore machines as presented categorically. So this, when I say classical, the original C and F appeared as early as 1962. So it's pretty old by now. Okay, anyway. Okay. But as far as I know, the representability of these kinds of behaviors was not observed until recently. Okay. So I will say also that I've seen it claimed by Eigel. I don't want to put Eigel on the spot or anything, but in private, that you can also adapt this to get stochastic differential equations, behaviors of stochastic differential equations representably. So not putting him on the spot, it's not public knowledge. It only goes out on YouTube. But that should probably work too. So, okay. I won't cover that, of course. I'm going to let him publish it. Okay. So with ODEs, we've seen that the ODE dt equals 1, which goes from R to R, where by this I mean just R equals R, the trivial bundle over R, represents solutions to ODEs. Okay. There's other kinds of behaviors we could also do, right? We didn't have to take those. Like, so in one, we could instead, we could take +1 id on Z mod n. And this would give us n cycles. We could similarly cook up something in the other examples as well. For example, in 3, we could take the canonical tangent, the canonical vector field, which I'll just call Ix on the unit circle. And this would give periodic orbits of period 1, or the radius of the circle, or not the radius of the circle, 2 pi the radius of the circle. Okay. So we can get other behaviors. So my point here is that other behaviors are similarly representable. Okay. The main idea in all of these, though, is that you always have to choose what happens on the interface first, and then you choose how to solve it. Okay. So, okay. So what we'll see is that this organizes into, so now we can finally come to the theorem. So if we have Jason, could you stop it again? Okay, so the question will be, how do we organize these behaviors and their compositionality into a single structure, a single construction. So for that, we will need this notion of a loose right module. But I guess before we go there, I'm going to start to talk about what we can actually prove about the compositionality of these behaviors. So so see, like their compositionality, like what do I actually mean by that? So what do I mean? Well, let's see what we have here. Suppose we have some kind of system here. S to interface I. I'm going to start writing things with simpler double categorical notation because remember that this is all takes place in a double category of lenses, right? And I have my clock here, which I'll write as C, and I'll just call it boundary C here. So this is my clock or my representative of behaviors, right? So given this thing here, some kind of chart I, we can then ask for, these are dummy back here. We can just sort of ask for, or maybe they're not. Here is C. State of C back here maybe. We can ask for a map here such that this is a square. That's again what representability means in the above case, right? If we go back up to here, then we have the clock, we have our system, we have our map on the interface, which sets a bunch of parameters, and then we ask, do we have what are our traces for this choice here? So this is how we can frame it. And now, if we have that, we can start to ask certain questions about compositionality, right? So one of the things we note, right, is that if I have any kind of composition pattern like this, I believe we did cover this, in fact. And we have any new thing in here, J, as long as we have a compatibility, which is the middle of this here, a square of this form, right? Then by composition in the double category, we get a new behavior of the composite system. Yeah. Mm-hmm. And also, right, quite evidently, if I have any up here, if I have here some other map of systems down here, let's call it phi, then I can compose and get a behavior of T like this. And these two things can interact by the interchange law of a double category. So if I have both of these at the same time, and the cell here right? Then the resulting composite, I can do two things, right? First, I could get the combined behavior up top. And then take the combined homomorphism down here. And then I could compose them vertically. Or I could do the opposite. I could take the combined homomorphism here, and then I could combine the compatibilities here. But either way I do this, I'm going to get the same thing in the end. This is just stuff we know because we know we're in a double category. But how can we express all of this in terms of sort of sets of actual systems? So the actual problem. And for that, we're going to have to go to use loose right modules to describe this as this. Because one thing I want to know is that want to note is that this is not exactly the same thing as representability in a double category, because we're not mapping out of an object of a double category, we're mapping out of a morphism in a double category, and we have to keep track of that morphism. Namely, recall that our systems are lenses. So they are these loose morphisms in this double category of lenses. So now we can come to a def is a loose right module of a double category. Right? So if D is a double category, okay, then we can express this as, so a loose right module consists of one for any, what I might call, well, I'm going to call it I instead of D because we'll often think of this as our interface double category for I and I, right? A set MI, a loose right module M consists of a set MI, right? For any tight IFJ, we have and M naught in MI, M1 in MJ, we get a set M, maybe M F, M naught M1. So we think of this as we will think of this as systems with interface I. We will think of this as homomorphisms of systems that act as F on the boundary. And then 3, for any, oh, and I should say, maybe before going on from 2, we have a composition plus composition for phi in, or, phi naught in M F I J, phi 1 in M G J K, we get phi 1 after phi naught in M G after F I K.
Sorry, is the I in the I'm expecting it to be MF like M0, M1 is a MFIJ.
I'm sorry. Yes, yes, that's right. M naught, M1, M1, M2, M naught, M2, right? So the idea is that we can compose morphisms of systems and identity. The identity of a system M naught acts as the identity on its boundary, right? So we can compose homomorphisms of systems, and when we do that, we compose how they act on their boundary. So this information, by the way, is known as a category displayed over the category of type morphisms in I. That's the information. It's equivalently, we have something called M, and we have a functor to I naught, the type morphisms in I, where M here is equal to what you might think of as sort of the Grothendieck deconstruction or the pairs. I'll just write it as pairs of an I and an M naught, where an M naught is in MI, or an M, not there, just M. And the morphisms are maps which are pairs of elements of from I to J, and a map from M to M prime, or M naught to M1, right? And this is the projection, the first projection. So it's equivalent to the data of such a functor. Okay, so in this case, by the way, this thing here is going to get a name. Well, just to be clear, right? We have I, M naught, and then a map here is F phi to J M1 is a pair of I to J F and phi in M over F of M naught M1. And that forms a category. That's sort of what we've asked for so far. So this thing has a name in here. This thing is going to be called the carrier of the module M. So M, of course, is going to have a lot of data, more than just what we said. But this is what's called the carrier. And if you think about it as a whole, it's a category equipped with this functor down to the types there, but it's the category of all systems over all interfaces. Right? Because the objects of M are a pair of an interface and a system in that interface. And a morphism is a pair of a map of interfaces together with a map of systems that acts that way on the interface. So in other words, M is the category of all systems. And what we've done is we've sort of sliced that category up over each interface. So we've given every system an interface. So then 3 is that suppose we have W, which is a loose in J. So we think of this as a composition pattern or an interaction between systems. Right? Then we get a functor, then we have blank dot W, which goes from MI to MJ. And then 4, and this should be, we'll describe exactly the laws this has to satisfy in a bit. Oh, one thing I'll note, maybe it's worth noting. One thing to note here is that if I look, every one of these MIs I said was a set, but in fact, we could actually consider it to be a category because we can always take F here to be the identity, And if you look at this composite rule here, right? If I take phi naught in MF and phi 1 in MG, I get a composite in MG after F. So if both F and G are the identity, then G after F is still the identity. And therefore, maps that act as the identity on their interface form a category for every interface. So I can consider this set as a category where the maps in that category are the maps which act as the identity on the interface I. And so I'm always going to do that. That is the category which is the inverse image of I under this functor. Okay? So having thought of that, I can then define this. So where we have now, we have, let's call it M dot W prime. I want an isomorphism between that and M dot W dot W prime, where W dot W prime is the loose composition in the double category. And similarly, I want M dot the horizontal identity to be isomorphic to M. And these isomorphisms should preserve the boundary. So it's not just that, it's plus coherences, the same sorts of coherences we talked about when we talked about double categories in the first place. Okay. And then 4, these two interact. So suppose I have this. Right? Something like that. Given this, right, what I want is I want to be able to take 4 phi in M over F of M naught M1, and let me call this C. I get C, excuse me, phi blank C in MG, M naught dot W, M1 dot W. So all of these laws can be made a lot more understandable if I note that I can always take, for any I can consider myself to have a sort of dummy domain and then put I'm going to do a double barred here, an M like this, and I'll take this to be notation. This will be notation for M is in the module over I. And then what we note is that the rules I'm writing down are all rules about, oh, sorry, I need another notation. And then if I have an F, and say here to I prime, and this is M naught, then I put another dummy domain here, and I put another M1 here. Then here, if I have a map here, will be notation for phi is in MF of M naught M1. So with this notation, it becomes very easy to describe what I've been describing before, because the first thing we can do is note that, well, I can stack these vertically. And that gives me a vertical composite or a tight direction composite for these things, which is what we talked about over here. And we note that what that tight composite is going to be, we take the tight composite over here, and then we take this is where we remember this is notation. This is where we get our phi 1 after phi 0. Right? So we have good notation like that. We also can do other things. So we also can take this m naught, right? And we can compose it by w. And this is what we got before, where we said we had a way to compose by these w's, like that. So this is what we were describing up here. We have an action by every loose of sort of multiplication on the right. That's why it's called a loose right module, because it's something which has a multiplication on the right by our double category, by the looses in our double category. Right? And that gives us a map like that. And then we also have a way to multiply these maps on the right. Which is what we discussed up here. And then what I can say is that the rules that govern this are exactly the rules that govern composition in a double category, which we've already seen, but where you just remember that some of these things are in dark green and some of them are in this sort of light pastel blue. As in, you just remember which ones are supposed to come from the module and which ones are supposed to come from the double category. Right? So you never put anything on the left-hand side, but everything that goes on the right-hand side is fair game. So in particular, we must have a sort of interchange rule, which looks like this. This can be reduced in two steps in two different ways. Right? One is that we reduce it, sorry, this needs to be dot w prime. This is m2 dot w prime. We can reduce it in two different ways here. This can then, by the above rule, give us the following. Or we could do it in the other way, right? So in this way, we did the loose composition first, and then we did the tight composition. But we could also do the tight first, right? And then we could reduce it again. And the law we need is that those two are the same. Right? And we also note that the associativity law I was saying here, This is very familiar from composition in a double category. So all the rules that govern this are just laws from composing a double category, but where we've actually marked just some of these things to be sort of special and on the right here, and we don't give them domains. Like they all, and one way to say this is that they all have the same sort of extra dummy domain here that we never touch. But they map into the things in our ordinary double category, which behave like a usual double category, and the laws that work are exactly the same laws as a usual double category. Right. So there's a couple ways that we could define this. But one of the easiest ones, I think, is that what we can do is we can say we actually have a very simple double category. So loose is equal to this double category, 0, 1, where I'm being very deliberate about this color choice here. And it has this very simple, it's a very simple double category with these elements and all the identities for them. But everything else other than this is the identity. So if we really wrote this out with all the identities, it would look like this. Where all, oops. So this is a double category here. It's determined by the fact that it only has, the only non-identity it has is this thing called 2, which goes from an object 0 to an object called 1. Right? And then what we could say is like, so the definition is that a loose bimodule is a double category M with a labeling functor L, which goes from M to loose, right? And a loose right module has L inverse of 0 being terminal. Having a unique object, which is this extra dummy here. So the way to think about that is that if we're up here, right, note that we were writing down all these diagrams and they all had all the same laws as the laws of a double category. That gives us a double category, namely this double category M. But we have to remember which things were in the module and which things were in the double category I. So what we do is we label it, right? And we say that L inverse of 1 is equal to I is the double category acting on the module. Right? So if when we label, it gets colored like this, you see that everything that would be in the module, so everything in I, these are the labels for I, and these here are the labels for the module. And the fact that we compose says that this gives us a valid sort of the fact that this is a double functor says that the labelings all line up. In other words, if you take something which is labeled by 2 like this, and you compose it with something that's labeled by the loose identity of 1, something that's labeled by 2, something that's labeled by the loose identity of 1, then their composite must also be labeled by 2 because this is a loose identity. And that's true. If I take this thing, which is labeled by 2, and this thing, which is labeled by the loose identity of 1, then their composite here is labeled by 2. As you can see, it has the green double mark, which is the same mark we put here that it would be labeled by. So this gives us a very nice ontology for systems. So this is our ontology for systems. Which is just the double category loose, but with other names, right? We have here system, or right, which is up there, it would be 2. We have here interface. Here we have interaction. And here we have interface again. And the fact, and over here, I'm just going to leave this as a dummy. We're not going to talk about the domain there because we're not going to need it for now. We could talk later about control systems, which give have a nice story if you have a domain, but I'm not going to do that right now. Okay. Interaction, interface. Okay, great. So then we also have map of interface. Oops, wrong color. So map of interfaces. And here's another interaction. And here's another interface. And here's another map of interfaces. And then we have here is a map of interactions. Also a compatibility. We might say that these maps on the vertical boundary are compatible with the interactions on the horizontal boundary. And then, of course, we also have maps of systems. So this is what we'll call our ontology for systems. As you can see, this is a description of a very small double category. We also have over here the identities on this that we just leave unnamed. Now it looks like this is a named thing that isn't an identity, but we have the rule that this is an identity in this very small double category. And what that means is that if I take a system and compose it by an interaction, I get another system. That makes sense. If I take systems, I interact them together, I get more systems. Right? It also says that every other thing but system is an identity in this diagram. So another thing that means is if I take a map of interactions and I compose it with another map of interactions down here, say, then I'll get a map of interactions. And similarly with these compatibilities, similarly with the maps of systems. And finally, if I take a map of systems and I compose it with a map of interactions, I get another map of systems. Okay. So as an example of this, you can see that if I ever have some double category, right? I can basically, if I have a double category, I can sort of restrict and just look at special maps between it and call those my systems. And then all the other maps, maybe I could take to be a different kind of map in the same double category to be my interactions. And then as long as they ultimately compose in the same double category, I can get a module like this. So as an example, if we take more machines are a module over lenses, right? Because why? Well, a Moore machine is a lens. So we're going to define Moore machine for the tangency over some interface I, right, is by definition going to be the lenses from T of some space to I. Right? So this is going to be the set of all lenses Ts to I in lens. So these are Moore machines, T Moore machines for our old friend, the tangency, whatever it is.
Yeah.
Okay. Right. So now why does more machine get acted upon by this? Well, as we've seen now, the thing we'll write up here, we've been seeing these diagrams the whole time. If I write TS here to I, and this is TS prime to J, right? Oh, and now I need more colors, right? And then we have our notion of map, like this. And then we can also act on it by lenses. And maps between lenses and get new maps between systems. So I suppose next time I'll do the stochasticity, and then we'll actually prove a representability theorem for these loose right modules, which will let us organize all of the maps of systems into a single morphism of loose right modules. Okay.